Hello, today we're going to talk about step functions. Step functions are basically used to make sure that the output of the function has an integer value. So in each of the functions that we're going to be looking at, the integer inputs are left alone, and non-integer inputs are taken to one of the two closest integer values. So this is going to be true for several different ways of doing this. One's going to be just rounding off, the rounding function. We'll have a truncating or integer part function, the floor, sometimes known as the greatest integer function, and the ceiling function. So we're going to have four different methods of these. And these graphs consist of a sequence of horizontal line segments which look like stair steps, hence the name. We'll also examine the Signum function, which also kind of has a stair step pattern to it as well. So the first example we're going to look at is the truncation function, or integer part function. And what this one does is it leaves the integer values alone, but it just simply drops off any decimal portion if you've got a non-integer. So the domain is all real numbers and the range is a set of integers. Okay, and so here's a graph of it, and let's take a look at what's happening here. And let's take a particular interest in what's happening first of all, for the integer values. So you'll see those as the big dots here, and those are left alone. You know, -5 is still -5, -4 still -4, 0, 0, 1, 1. So those are on the line y equals x there, and they leave, like I said, they leave those integer values alone. But if you've got a number like 1.3, it just becomes 1, or 2.7 just becomes 2, or 0.1 becomes 0. -0.1 also becomes 0. 0.3 becomes 0. -0.2 becomes 0. And then, so that's right in here. And then, like -1.7 becomes -1. Okay, you just drop off the decimal part. So these are little steps that are like this, little horizontal line segments, and all of them have a length of 1, except this one right here, centered at 0, it's twice as long as the others. So notice that when you're to the right of 0, when you're talking about positive numbers, these will basically be rounding down, whereas if you're to the left of 0, a negative number, they round up for the numbers that aren't integers. So notice for the positive ones, these little line segments have a solid dot on the left and an open dot on the right, whereas the negative ones have a open dot on the left and a solid dot on the right. And then of course this one that's on the x-axis, it's sort of a combination of the two. It has one of the negative intervals with an open dot on the left, solid on the right, and one of the positive intervals from a solid dot on the left, open dot on the right, sort of put together, so it's now twice as long, and it ends up with open dots on both ends. Okay, that's one way we can do it. Just drop off the decimals. This is built into your TI graphing calculator. Here's the TI-84 screen as iPart. And you can find that by hit the Math menu and then right arrow to Number, Num menu, and then go on down and you'll find it down in there somewhere. So we put this in as y1, the integer part of x. I picked a window here going from -5 to 5 for both x and y, and you can see the graph there. What's hard to see is the part of the graph that's on the axis right here, from -1, 0 to 1, 0. The other thing that you can't tell by looking at the graph is whether you have solid or open endpoints, but that does show up in your table here. And so you see, for example, -0.5 is mapped to 0, 0 goes to 0, 0.5 is 0, 1 goes to 1, -1 goes to -1, and of course you can scroll up and down this table yourself to see a few more examples. Now, of course, probably the most normal way we convert to integers is by rounding off. And so the idea of rounding off is just to go to the nearest integer. And so notice, if you look in here closely, any of these values in this solid line here are closer, the x values are closer to 1 than they are to 2 or to 0. Now there's one that's a tie, and that's if it's exactly halfway in between. There's actually two that are tie. One, this one at half is exactly a tie halfway between 0 and 1. And of course this one on this side at 1.5 is exactly halfway between 1 and 2, so they're equal value. What we always do with those is round up. And the reason why we do that is to make a nice simple rule. So if you have 1.500000007, it's still closer to 2 than it is to 1, so we should round that up. So if you want an easy rule, you can still just look at the digit in the tenths place. If it's 5 or larger, we'll round up. Okay? And so this is the standard way for rounding off. Okay? Not rounding up or rounding down, but rounding off. And this is called the rounding function. Of course, we can generalize the rounding function to round to the tenths place or the hundredths place or the thousandths place. And we do this sort of thing all the time. Or even to the tens or hundreds or millions or whatever. But this is rounding off to the nearest whole number, well, the nearest integer, actually. And again, you can see some of these here. Notice some differences in the table here. Truncation, we just drop off the decimal. So these guys between 0 and 1, all these here just become 0. And these guys here between 0 and -1 also become 0. You just drop off the decimals. Here we just drop off the decimal, the 2, 5, or 8. We just drop it off. Whereas over here, if we're rounding off, now if it's 5 or bigger here, we go up. So that goes up to 1. 0.8 goes up to 1. But 0.3 goes down to 0. Of course, the integers are left alone. 1.2, it's not 5 or bigger, so it goes down to 1. 1.5 and 1.8 are going to round up to 2. And so we can see this. So 1, the integer values, or the line y equals x, would go right through the midpoints of all these line segments. 1, 1, 2, 2, 3, 3, 4, 4. Okay, another way we can do this is a function called the floor function, or sometimes called the greatest integer function. And there's a couple of different notations you'll see for it. When you see this thing with the sort of double bars on both sides, this kind of with the bracket and then a kind of a double thick bracket, that's what we would call the greatest integer function. And you see it this way with a bracket with no top to it but a bottom, that's called the floor function. They're the same function, just two different notations and two different words for it. And this always rounds down to the nearest integer that's less than or equal to the input. Okay? Notice in all of these cases, functions we're doing so far, the domain is all real numbers, but the range is just the set of integers. So this always rounds down. Okay? So notice for a positive number, the floor and the truncate are the same for a positive input, or even for 0. And of course, any integer input, truncate, floor, ceiling, which we're going to do in a minute, and rounding are all the same thing. It doesn't change the integer values. It's just a matter of what do we do with the ones that are between the integer values. And so here we get this, and of course the graph is the same for that, for the positives as it is for the truncate, but for the negatives it's not. So here these round down to 0. Anything 1 point anything rounds down to 1. 0, 0 point anything positive rounds down to 1. But a negative between -1 and 0 rounds down this time to -1. And -1 point something rounds down to -2. This is built into Graphmatica, and actually it's built in both ways, as floor of x or as the greatest integer of x, int of x. And TI graphing calculators is built in as int of x. You can find that again under Math Num or TI-84. And here's the graph. Unfortunately, the axis is the same color as the graph, so you can't really see this part between 0 and 1 very well. And of course, when you see this graph in Graphmatica or on your calculator, you don't really see the endpoints, whether they're included or not included. However, you can generate tables in either case, like I did here, for the graph here, and we could find out this. So this is a graph from -5 to 5 on both x and y, and you can see the graph there. Again, it's on top of the x-axis right here between 0 and 1, and by looking at the table you can see what it's doing in terms of rounding off for those between 0 and 1 and those which ones are included and not. For example, -1 goes to -1, so there's a closed dot right here at -1, -1. There's an open dot at -1, -2. The ceiling function is built into Graphmatica as ceiling of x. Where is the, did I skip a slide? There it is, it's just out of order. The ceiling function rounds all numbers up to the nearest integer. So remember, we use this notation here with the bracket without a top, that for the floor, so then you might see that we'd use this notation here for the ceiling function, and it rounds all real numbers up to the nearest integer that is greater than or equal to the input. So now we go up. If it's an integer, leave it alone. So now those integer values, again, are going to be solid dots on the line y equals x. And those are the big dots that you see here. But then the lines kind of go to the left of that, line segments, because between 0 and 1, you're going to round up to 1. You're going to go up to the ceiling being the next highest. So the ceiling is like the next highest integer, and the floor is the next lowest integer. Okay? Now you can compose step functions with other functions to make sure that your outputs are integers. For example, here's a graph of y equals floor of x squared, or in other words, the greatest integer of x squared generated by Graphmatica. So here you can see kind of you can kind of still see the x squared shape, which hits at 0, 0, 1, 1, 2, 4 here, and so forth. Okay, and you can see that, but then you also have some things that are in between that are integers, so you only get integer values here. Kind of compare and contrast the floor function of x squared on the left versus y equals the ceiling function of x squared on the right. So values actually on the x squared function, values between -1 and 1 are not including -1 and 1, are values less than, they're between 0 and 1. So when you do the floor function, they get pushed down here to the floor of 0, so they're on this line segment there. Oops, back up. Whereas between 0 and 1, if they're the ceiling function, then they're pushed up to 1 here. You can see that here, all of them together. And so here's y equals x squared in red, and then you've got those other two functions all graphed on top of the same graph. And notice here, between -1 and 1, again, the floor is down here, ceiling is up here. And let's just look in between -1, or between 1 and, let's see, well, actually it's the square root of 2, right? So between 1 and the square root of 2 for x, then this part of the graph is between 1 and 2 on the y of the graph. And of course the ceiling of that would be 2, so that would give you these brown little segment right here from, I guess that goes from 1, 2 up to square root of 2, comma 2. And the ceiling would push it down, that's the ceiling. The floor would push it down below, down to 1. So that's a line, horizontal line segment again going from 1, 1, and then this is square root of 2, comma 1. And you can look at any of these, any pieces you want to be looking up and down here. And notice that the y's are in between here if you just do x squared for y. And then ceiling will round those up or round them down. In all cases, these dots that are on the integer values, you know, where these little line segments meet, they're going to be a solid dot right there, open dots on these outer edges out here. Here's the same thing for floor of x cubed, ceiling of x cubed, y equals floor of x cubed, y equals ceiling of x cubed, and y equals x cubed. So again, you can see, for example, between 0 and 1, we get y values that are between 0 and 1. So they're pushed up to 1 for the ceiling and pushed down to 0 for the floor, and so forth. One other function we'll look at is, sometimes we're only concerned with the sign of a number, whether it's positive or negative or 0. And so the sine function or signum function, sign of x or sgn of x, two different ways to say that, is actually a piecewise defined function returning -1 if it has a negative input, 0 if it has a 0 input, and +1 if it has a positive input. Now be careful when you're saying this, because this sounds almost the same as, it sounds exactly the same as the sine or sin function from trigonometry. That's also called the sine function. And usually if you say the sine function, you're talking about the one from trigonometry. So that's why we call this, instead of calling it the sine function, sign, we call it the signum function. So you should really pronounce this the signum function. And notice what that is. That if x is positive, then that gives you +1, which is a horizontal line or ray, half of a line, going there to the right. That's the first quadrant. And then in the third quadrant, we've got y equals -1 for the negative inputs, and both of those have open inputs, open endpoints. And then if x equals 0, you get the origin there. So after completing this, you should be able to do the following with and without technology: state the definitions and produce tables and graphs for step functions, including the truncation, integer part, the floor, the ceiling, the rounding, the signum function, and understand the effect of composing one of the step functions above with another function. Now I do want to show you one more thing before I finish up here. Let's see, where am I? I want to pull open a Sketchpad file. Okay, let me find it here. I have a Sketchpad file here for a survey of families of functions, and it actually has lots of different functions that we can study, some from probability, some from this course on power functions that we've studied about recently, constant and linear functions we studied about earlier, other polynomials, second, third, and fourth degree polynomials, exponential functions we'll do later, trig functions that you might study in trig class, and some of this. Right now I'm going to go to this step function. There's the signum function. Whoops, there's one we need to hide down there. That's not part of it. And let's compare a couple of these. So compare the ceiling and the floor, and you can kind of compare these next to each other and see what happens. So between 0 and 1, look at them this way, up and down. So between 0 and 1, the floor pushes it down to 0, and the ceiling lifts it up to here. Of course, if I also graph let me do this. That's the line y equals x. What do we want to make? Let's make it, no, I don't like that. We'll make it orange. Okay, so this is the line y equals x, which is also known as the identity function. Okay. Okay, and you can see that there. And so notice that the points on the line y equals x, okay, are on both the greatest integer or floor function and the ceiling function. So the floor and ceiling, those points there that they have in common, you can see. So let me hide both of those. Here's the rounding function. And notice that the line y equals x goes right through the center of the intervals there. So we're rounding off. compare that to, say, the floor function, and notice that there's overlap, but not the same. Now let's look at the truncation function. Now here's truncation and the floor. And notice the truncation and the floor are the same here for positive x's. Those are all the same, all of this. But the negatives, they're out, they're shifted. So the floor is always going to go down, so it's the green ones down here. But the blue lines up above that, blue line segments above those, are the truncation. But truncation is the same when you have positive. And notice that truncation and ceiling are the same for the negatives. So they're here, but they're shifted from each other here vertically for the positives. Okay? Alright, so I think that gives you kind of an idea of what's going on with this. Let me also show you this. When you're in Graphmatica, you can go to Help and go to the operator table. There are lots of things that you can, basic operations here, but they have some built-in functions like absolute value of x is ABS. Ceiling is, you spell it out, ceiling. Floor, you spell out floor. Integer is the greatest integer, also noticed. Same thing as a floor, so an alternative there for that. It doesn't have some of the other things. It doesn't have truncate, for example. But we could do, so you could do y equals floor of x to get that. But you could also do y equals floor, well, let's clear that out. Okay. And of some other thing, say x 3x plus 2. So if you just did y equals 3x plus 2 without the floor, that's going to be on one side. So those sides, that side of the little line segments will all have solid dots, and the other side will have open dots. Okay, so you can easily combine some of these things using Graphmatica. On your calculator, okay, you have some of these things built in under math, number. You have an integer part. You also have a fraction part. The fraction part is sort of the opposite of the truncation. It just knocks off the left of the decimal, and so you're just left with the decimal part, and that's the F part, the fraction part. If you do integer part, it knocks off everything to the right side of the decimal and keeps the other side, and then it keeps the sign positive, negative, just like it is. So it's neither rounding up nor down. Depends on whether you're, whether you're in the positives or negative, whether you're rounding up or down. But it always just knocks that off. Number 5, int, is the integer part, and notice we do have round also. You see that up there? And so we can do round. And I think round on this one, on the calculator, you specify, let's see what happens here. Okay. I think you give it another, yeah. So this says 0 decimal places. And if we were to do like that, that's going to round to no, it's rounding to, yeah, to 3 decimal places. It's still 3 decimal places because it's 2.460. Okay, so it's still there's a 0 there. It's not writing, but it's 3 decimal places. So there we go to 4 decimal places and so forth. So you can specify how many decimal places. I don't know if it's going to do this or not, but let me try something here. What happens if I put in this? I'm wondering if you can do something like this. What if I put in -1? Will it round? No, it won't do it at all. So it won't round off to tens or hundreds or thousands, but it will round off to tenths or hundredths or thousandths, or to a whole number. So you put how many decimal places you want there, and you can't put a negative in. Okay, and then you can do, so that's rounding. Again, integer part, you can use that. And we get, it just lops that off. Okay, and we can do integer part. That just lops it off, and then greatest integer is the floor function. So this will be the floor. So this will go down, and if I do, whereas this one is still going to go down to 2. Okay, so some of these functions are built in your calculator. You can use those on your calculator to you know, figure out things if you need them. And I don't think the Signum function is in there on this calculator. I don't think. So you'd have to work at trying to get at it some other way. Okay. Let me show you something too, though. If you take an x value and then divide it by the absolute value of x, that gives you the Signum function for positives and negatives, but it doesn't work for 0. It's just undefined for 0. So that would be one way to get at the Signum function, except for 0. Okay, I think that kind of wraps up that, and we'll move on from here.